Thank you. Nice to meet you. First of all, I would like to give thanks to Professor Eun for inviting me at this nice university, KAIST, one of the best universities in Korea. Today I'm gonna talk about the finite field Erdős distance problem. Let us see our outline of today's talk. We will review the definition of Erdős distance problem, both in Euclidean case and finite field case, and then conjecture. So I will introduce some basic skills how to get distance results in the finite field setting. Moreover, I'll briefly introduce restriction problem for sphere in the finite field, which is one of the central topic in Euclidean harmonic analysis. So I'll show you some connection between these two problems, Erdős distance problem and restriction problem. Finally, I will introduce certain result, best known result in this problem. I think after this talk, that you know how to improve this result. Okay. Maybe 70 years ago, Paul Erdős addressed the question: how many distinct distances can be determined by finite subset of Euclidean RD? So here is a distance set, given set E, finite set. We take 2 points from set E, then we measure distance, right? So distance set is easy to define, right? So what is the question? Given finite set, we wanted to determine the smallest exponent alpha, such that the minimal size of this distance set is approximately e to the certain exponent alpha. So if this alpha is big, the result is good, right? So problem is like that. On the plane, I will take some E, it's just a 3 point. In this specific case, what is distance? Minimal distance. What is the minimal distance of this distance set? In the case when size of E is 3.
One distance.
Exactly 2. Zero. Zero distance happen, right? So, yeah, it's easy, right? However, 4. How about 4? You may
2.
the size of E is 4. You put, right, this 4 point on this rectangle, right? So is it equal size? So 1, 2, 1, 2, 0, 3, right? This is the worst case, right? This gives us answer for specific case. What if size of E is huge, large, 100, 1,000, 1 billion? It's not easy to answer this question. But you may guess that, oh, this problem is easy because given endpoints, you may put this endpoint on unit circle. Equal distance, right? Like that. Okay, unit distance. There are endpoints. Then you can measure 1, 2, 3, like that. Right? We can exactly count the distance determined by this point, right? You may guess this case gives us answer. First, I thought about that. This case gives us answer, the minimal low bound. in fact, this first worst case is you put it is lattice point. You put endpoint here on the lattice point like that. This gives us smallest distances. Which is conjecture. So Erdős consider endpoint which is arranged on the regular polygons and subset of integer lattice. Then he count some distance with this set. And then by using number theory argument, he compute size of a distance set is approximately like that. In this case, the higher dimension is this. That was a conjecture. Roughly speaking, the number of in dimension 2, the size of a distance set is almost same as size of E, right? Up to logarithm. Surprisingly, recently in 2010, Gus and Katz just posted some paper on arXiv. They proved that the minimal distance of this distance set is size of E divided by log of size of E. If you compare this conjecture, almost sharp, right? Up to logarithm.
You always have D bigger equal 2. If you have D equals 1, you're on the real line. Is it obvious that this is trivial? I don't think it's trivial.
One-dimensional case. We are not interested in one-dimensional case.
No, but I mean, what would be the answer? I think it's not completely obvious.
Obvious, yeah. Because it's arithmetic geometry gives us minimal distance. Yes, we are not interested. We can easily prove, right? I cannot prove, but I can prove maybe if I have time, right? So we are only interested in the case when the dimension D is greater than or equal to 2. So in dimension 2, these Gus and Katz results are very strong, right? It's almost sharp. Higher dimension, but however, higher dimensions, the result is like that, but this exponent is 2 of these conjectured one, right? But the best known result is not so good compared to conjectured result. Okay?
When D is large, it's quite good, no? Getting closer and closer to the
Okay, so in 2004, Wolfgang Katz and Tao just introduced a model problem of this Erdős distance problem. I mean, in the finite field, they replace the Euclidean space by finite field space. Okay. Now let me introduce some notation in finite field setting. FQ denotes a finite field with a Q element. Q is just a power of other prime. Okay? So characteristic of the FQ is greater than 2. FQD denotes usual D-dimensional vector space of finite field. Like Euclidean case, we can define distance set. Let us look at this one. Given set E in FQD. So in the finite field, its x-axis is like FQ, right? This is line. One line head contains just Q element. The other axis is Q. You can find some strange one with this definition of distance set. What is that? Like a norm notation. Here there is no square root. Why? Not all elements of FQ are not the square root. We are only interested in counting the number of distinct distance, right? So it does not matter. In fact, this is not norm in finite field case. But rotation invariant, right? So Borg has Tau just introduced this distance set. With this distance set, we can ask us some similar Erdős distance problem in finite field set. Given set E, find the minimal cardinality of this distance set in terms of size of it. So what's the conjecture in finite field? If there is no difference between the Euclidean conjecture and finite field conjecture, we may guess, right, here, in finite field case, okay, in dimension 2. This is what? Looks like, right? E to the something blah blah, right? 1 minus something blah blah, right? Logarithm.
Doesn't it maybe make more sense to look at the difference set instead of the distance set? So if you're working over some finite field,
Yeah.
Instead of looking for, I have a set of vectors, instead of worrying about their distances, I just look at their differences. Those differences are going to be, again, elements of my...
Yeah.
You mean yeah.
Yeah, but instead of...
Yeah, you can.
norm.
Yeah, we can. Yeah. You can choose any polynomial like that. Here, distance relate to this polynomial, right? Right. It's a good question, right? You can choose any polynomial.
Sure.
Then we can work this problem. Okay, right. In
Planar one. You
Yeah,
can
yeah.
also change the norm there.
yeah,
It doesn't
yeah.
have to be
In fact,
Euclidean norm.
Sure.
yeah. In fact, we generate this problem. In fact, for a few years ago, we generate this problem, but we are not interested in. Scale is almost same, right? Key estimate is like the same. Key fact is the same. Now let's see. So in finite field setting, Bolgain tau Kac get 1 over 2 only. Here, 1 over 2. 2 small, right? 2 small, right? This is conjecture, right? Like this. After logarithm, right? In Euclid case, in dimension 2. 1, right? Here, power. Exponent is 1. They got 1 over 2. You may think this result is very weak, right? But not weak. The method is very beautiful. They got this result. They use a combinatoric argument. I mean, as I know, they use additive combinatorics. But they put a certain assumption. First assumption in dimension is 2. Now, they put this assumption, prime field. And -1 is not a square number. Not a square number, right? This. There is not a square number such that I square is minus. They assume this means, right? Q is 3 modulo 4. This means there is no square number. -1 is not square number. Okay, they got this result. Moreover, it's very hard to find the connection, concrete relation, delta and epsilon. Given epsilon, we cannot find the delta. I mean, we can find the delta, there exists delta, but there is no concrete relationship. I mean, there is, but they usually, it's very hard to find in their, according to their proof.
So this constant C, does this depend on Q
No.
or is this absolute?
C is independent of Q. I mean, yeah, C is uniform. Okay, usually C depends on dimension, but dimension is 2, right? Here, the important point is that the constants is independent of Q, size of finite underlying finite field. That is that good point, right? Main point. Okay. Let's move to what happened. This Erdős, this conjecture in Euclidean space cannot be true in the finite field case. If there is no assumption on finite field. Now, for example, let us see easy example. Here is assume there is -1, such that I scale. -1 is a scalar number, right? We assume. Then just take this set in two-dimension space. This is a line, right? So size of E, cardinality of E is just Q. It's trivial, right? If D is 2, D is Q, 1 is equal to D minus D divided by 2, right? However, you can easily check the distance is just zero. So Erdős distance conjecture in finite field is easy, right? We can say the exponent is 0, right? We can say only 0, right? We cannot improve this trivial result, right? If we take this example, this exponent must be 0, right? It's a trivial problem, right? So we have a problem. Moreover, if you take subfield, if its Q is certain prime P square, its Q is prime, then this is a subfield of FQ, right? What happens in this case? Take E is a subfield, FP times FP. Let's compute the distance set. Size V is okay, P square, right? And Q. Q means Q of 2, P of 2, right? What is distance set? Subfield. Subfield. P, right? I mean, this is M as this one. Total set. Distance, because it's subfield, right? F is subfield of F is subfield of F of P square. Then distance must be contained in F of P. So then what happened? This is P, right? With this example, if there is some subfield like this, we can say that delta of E is certain to be oh no, how much? I think square root, right? Let's compare in dimension 2. Then what is that? E to the, this exponent is what? 2 to the d, right? D of 2. Right?
D.
D, 2 of D. 2 of D? D of 2. I'm sorry that, what if dimension, let me put the FP, right? Like FP.
So 1 over D, right?
Yeah.
So 1 over D.
1 over D. 1 over D? Sorry about that. Oh.
Right, yeah.
No, 2 over D, yeah. So, this, in general case, Borgen, Katz and Taos results is never happen, right? General case. They claim that this exponent is greater than 1 over 2. But in this case, this exponent cannot be greater than 1 over 2. So we cannot extend this finite field case to in general case. For example, -1 is scale number. -1 is scale number case. So we have problem, right? So Iosifovich Rudnev just reformulate this problem as follows. Oh, introduction here too much. Let's see. If it's so filled, it's so filled, right? It's so filled. Pills. Let's take is how much? FQ D. D times, right? As before, we can measure size of is P to the D. It's Q to the D over 2, right? However, the size of distance set is P to the D. Oh, P is square root Q, right? This cannot be similar as all distance, right? The absolute value indicate the cardinality of distance set, right? Cardinality of set. Okay.
Yeah,
So question is that how much bigger set do we need to assure that our distance set makes all possible distance? So with this size, we can make only few distance, right? Compared to all distance. Okay? So Iosifovich Rudnev asked for the minimal cardinality of the set in general case, such that our distance set contain almost all distances, almost all possible distances. Okay?
Oh, I see. Some constant time.
Yeah, constants.
Constant.
Yeah,
0.1.
yeah. So you can choose any. So according to this example, what's your conjecture? At least our set must be bigger than this size, right? Oh, yeah, deal. So here is now new problem. According to this example, we can conjecture if the size of E is much bigger than Q to the D over 2, right? Then in fact our this size of distance set is similar as Q. Q means all distance, number of all distances, right? Okay. In fact, you take here one more point, right? One more point, like E union, like some like X is not here, right? X not here, right? But X in FQD. The conjecture says the size of this distance set is much bigger than Q. Right? Strange, right? We just add 1 point to here. The cardinal of distance increases a lot, right? It is conjecture, but this is conjecture. Reasonable, right? According to this example, right, the conjectured exponent is D over 2, right? But this conjecture is false in general, in the case when the dimension is odd. 2011, we construct some example which show that this conjecture is false in other dimensional case. In fact, Josip Rudnev got this exponent. D plus 1 over 2 is enough to get all possible distances. Okay? This result. It turns out that this theorem is sharp in other dimensional case. Okay? However, we still believe the previous conjecture is true. In the case when dimension is even. I mean, if dimension is even, we beat this exponent. I mean, we can reduce this exponent to D over 2. Okay? So nowadays, we are only interested in the distance, Erdős distance problem in even dimensional case. Okay? In other dimensional cases, the conjecture was solved, right? So get this exponent, D over 2. What if dimension is 2? This exponent gives us 1, right? It's line. If size of E is greater than number of elements in line, then we get all possible distances, right? So this is conjecture. Actually, the sharp exponent in other dimension, this one, right? We can improve in dimension 2. Here, today, I will introduce how to get this result. if E is a subset of FQ to the 2, right? Two dimension. With this exponent, power of 3, we get all possible distance. You know, 3 over 2 is smaller than 2 over 3, right? 3 over 2. So we beat the sharp exponent this in other case, other dimension. If dimension D is 2, right? However, higher even dimension, we still this D over 2, D over 1 over D plus 1 over 2 is the best known result. The dimension 4, 6, 8. Okay. So let's just introduce a new Erdős system problem in the finite field setting, right? Okay. So now let me introduce some another thing. Is how to get it. What is the basic idea? Right? Essentially, we use a free analysis, discrete free analysis. So how to change this discrete problem to free analysis problem? That is your question, right? Yes. Let's see. Given E, we wanted to find the size of E, right? Such that this distance set contain almost all elements of FQ, right? What is the minimal size of a distance? To assure that our distance set contain almost all elements of distance. But we consider counting function VT. Let's look at this definition of a counting function. A fixed t, then we count a pair over E, right? X, y, such that distance between X and Y is t, right? What does it mean of the mu t, counting function? Counting function value indicate how often single fixed distance happens. For specific t, if mu t is large, very large, what can you guess about distance set? We cannot get many distinct distance, right? That is ideal. So our guess is that if size over E is much greater than Q to the D over 2, then mu t is independent of t. I mean, equivalently distribute. I mean, right? That is actually correct. This guess is conjecture. Okay, let's see. So let us check that if this mu t counting function value is positive for some t, then t must be contained in distance set, right? Look this. We can find some pair such that these 2 points determine the specific t, right? Distance set must contain 0 element. So from this observation, we have this lemma. If counting function value is positive for each fixed t, we know t is 0, right? T is trivial. What does it mean in this assumption? Each element contained in distance set, right? So we get this conclusion. Alright? In other words, look at this assumption. When this is true? When is this true? Determine size of E, right? Such that for each non-zero t, this counting function value is positive. Okay? So if we can estimate void t, so our task is to estimate this void t, right? To decide the size of this E, we need to estimate counting function value. We can write this counting function value, this size, the kernel of this set. We can write like that, right? Sum over x, y in E such that here st, we write this st for indicate function on set st. I mean, we use simple notation. This is not set. In this case, the function, right? Indicate function. Does it make sense? Does it make sense? Now we use Fourier analysis, Fourier inversion theorem, something blah blah blah, and definition of normalized Fourier transform. There is some definition, and we can convert this to this amount, like that. This amount. Fourier transform, and this is Fourier transform on sphere. St. Oh, St is, what is St? Looks like a sphere, right? We say this t is radius, right? T sphere, okay. Then we separate two terms. This m equal 0 case, m is not 0 case. This is main term. This is remain term. What is our goal? To find some size of E such that this total number is positive, right? Right? Then the first term should be positive. Like that. It's easy to compute. The absolute of remain term is like we can estimate like using pre-analysis. L2 estimate, blah blah. We get some upper bound of absolute value of remain term. If the main term m is greater than absolute value of remain term, what happened? What happened? Void t must be positive, right? So we get this condition. This condition sure that this is true. So we get, if you solve for E, size of E, then we get this condition. Right? This is the basic approach. In fact, routinely when your speech like use this method, then look at this conclusion. Conclusion is very powerful, right? Conclusion is very powerful. We get all distance, right? We don't have to get all distance, right? Almost all distance. We need, right? To get, okay? The time is... Now let me introduce another method. Oh, sorry about that. We follow previous argument, like that, blah, blah, blah. Now, key observation is like that. Look, sum of all t counting function. What is that? What is that? This is Vt. If we sum of t in FQ, should be all choice. This is given. Right? Do you follow this way? And then here same as t must be, if Vt is 0, if t is not in this set, so this same as the distance set. This by t. Then 1, right? We use coefficients. What happened? Coefficients. Let us take scale number like coefficient. Coefficients. Then what is that? One scale is the size of distance. Our distance set is 2, right? 1 of 2 is counter function. We dominate t is fq by t square and square root. We get this inequality. If we take a square both sides, right? You can solve for this one, right? This guy low bound is what? This guy low bound is we get the same as a to the 4 and sum over t in fq mu square, right? We get distance formula. Our goal is to show that this is much greater than similar as q, right? We want to determine size of E such that this inequality holds, right? But it's not number. What do we need? What do we need? Upper bound of this one to get low bound. That is basic idea. But here, I subtract negative V0 here. Why? There is some idea, very big issue, right? There is another idea. Like we start with the take out the minus V0 here. Technical problem, we just eliminate the V0. It's a very difficult deal with V0, essentially, right? So it is another idea. Follow same idea, we get some formula, distance formula, right? This is distance formula. So our main task is to get a good upper bound of this guy, L2 estimate, right? If we use Fourier analysis, maybe we can estimate this upper bound of this guy. In fact, we get certain formula. Okay? I don't like to introduce in detail because it's idea like that. But essentially, you just we get this formula. Our task is get the good upper bound of MEQ, right? MEQ can be dominated by this strange term, which exactly relate to Fourier transform, right? L2 estimate. Domain is restricted to what? Sphere. T is non-zero sphere, right? If this is 0, this estimate is this upper bound is very bad. So technically, we eliminate 0. This is one of the ideas. After we find this formula, right, we realize that we need to eliminate this for 0. Okay. If this t is 0, the quantity is very big. Otherwise, this quantity is small. This is actually related to restriction problem. So some restriction problem gives us like that, determine certain this quantity and this quantity. Exactly this quantity, the LR norm of the F hat relate to previous this. This quantity, right? This quantity is related to left hand side of this quantity. Okay, essentially applying the Fourier analysis, maybe we get good, upper bound of this guy. And plug in here, upper bound here, and then we get some number. In summary, we get this formula. This formula Now, we want this right-hand side is similar as Q, right? When this is true, if this term is greater than or equal to Q, right? Then this quantity is Q, right? So that condition gives us this one. This condition gives us. This condition implies that this quantity is greater than or equal to Q. So this low bound is Q, right? So we need this exponent. If LP, L2 estimate hold, then we get this result. So if P is big, result is big. Okay? I mean, it's funny. Essentially, we studied the restriction problem, LP, L2 estimate for sphere. This is conjecture. There is some conjecture. If the base is 2, we have a certain conjecture, right? Unfortunately, we could not solve this conjecture. However, in other case, we solve this conjecture. In other case, this conjecture gives us exactly t plus 1 over 2 result. As I told you, in other dimension, this is sharp, right? So we solve this conjecture for restriction in other dimensional case. In this case, we get this one. So we get this Erdős distance conjecture in other dimensional case. However, in even dimensional case, we get more. If we compare these two numbers, this is better. Unfortunately, in dimension 2, we solve the restriction props conjecture for sphere. In dimension 2, we solve the conjecture. So we apply the restriction problem for sphere circle, actually. If dimension D is 2, we get this 4 over 3, which is better than this exponent. However, D is greater than equal to 3, then we still have this D plus 1 over 2. So to improve this guy in even dimensional case, we need to improve restriction result. This is conjectured one. If P is this guy, if we plug in this guy here, we get this exponent. I mean, if we solve the restriction conjecture for sphere in even dimensional, then we get this Erdős distance result in even dimension. However, still this result is, this exponent is worse than D over 2, right? This is conjectured one. In other words, if we only use restriction estimate, we cannot solve Erdős distance conjecture in even dimension. However, we can little bit improve Erdős distance result, right? If we improve restriction result for sphere. When you study higher dimensional subject, Fourier analysis is very powerful, I believe. Do you agree? But in the low dimensional case, dimension 2 and 3, like combinatorial argument is very powerful. In my experience, right? Just sorry, I thank you very much for your attention to me.